The match control flow construct. Um, Rust has an extremely powerful control flow construct called match that allows you to compare a value against a series of patterns and then execute code based on which pattern matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of patterns and what they do. The power of a match comes from the expressiveness of the patterns and the fact that the compiler confirmed that all possible cases are handled. Rust has an extremely powerful control flow construct called match that allows you to compare a value against a series of patterns and then execute the code based on which pattern matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of patterns and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. Think of a match expression as being like a coin sorting machine. Coins slide down a track with the variously sized holes along it. Coins slide down a track with the variously sized holes along it. And each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match, and the first pattern, the value fits, value falls into the associated code block to be used during execution. Speaking of coins, let's use them as an example using match. We can write a function that takes an unknown United States coin and in a similar way as the counting machine determines which coin it is and return its value in cents, as shown here in listing 6-3. Coin, enum, and then using match coin. Okay. So coin is coin time and then coin is thing. Okay. So let's break down the match in the value in cents function. First, we list the match keyword followed by an expression. We list the match keyword followed by an expression, okay? Which in this case is a value coin. This seems very similar to an expression used with if, but there's a big difference. With if, the expression needs to return a Boolean value. But here it can return any type. The type of coin in this example is the coin enum that we defined on the first line. Next are the match arms, and arm has two parts, a pattern and some code. The first arm here has a pattern that is the value coin penny, and then the arrow operator that separates the pattern and the code to run. The code is, in this case, is just a value 1. Each arm is separated from the next with a comma. When the match expression executes, it compares the resulting value against the pattern of each arm in order. If a pattern matches the value, the code associated with that pattern is executed. If that pattern doesn't match the value, execution continues to the next arm. Much as in a coding sorting machine, we can have as many arms as we need. In listing 6-3, our match has 4 arms. The code associated with each arm is an expression, and the resulting value of the expression in the matching arm is the value that gets returned for the entire match expression. We don't typically use curly brackets if the match arm code is short. We don't typically use brackets if the match arm code is interesting. Short, as it in listing 6-3, where each arm just returns a value. If you want to run multiple lines of code in a match arm, you must use curly brackets and the comma following the arm is then optional. For example, the following code prints lucky penny every time the method is called with a coin penny, but still returns the last value of the block one. Makes sense. Patterns that bind to values. Another useful feature of match arms is that they can bind to the parts of the values that match the pattern. This is how we can extract the values out of enum variants. As an example, let's change one of our enum variants to hold data inside it. Another useful feature of match arms is that they can bind two parts. They can bind to the parts of the values that match the pattern. Match arm is that they can bind to the parts of the values that match the pattern. This is how we can extract the values out of enum variants. As an example, let's change one of our enum variants to hold the data inside it. From 1999 through 2008. The United States minted quarters with different designs for each of the 50 states on one side. No other coins got state designs. So only quarters have this extra value. We can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we've done here in listing 6-4. So we can inspect the state in a minute. Coin, penny, nickel, dime, quarter, US state. Okay, in the United States. Coin enum in which the quarter variant also holds a US state value. Let's imagine that a friend is trying to collect all 50 state quarters while we sort our loose change by coin type. We will also call out the name of the state associated with each quarter, so if each one our friend doesn't have, they can add it to their collection. In the match expression for this code, we add a variable called the state. In the match expression for this code, we add a variable called the state to the pattern that matches values of the variant. Coin quarter. When a coin quarter matches, the state variable will bind to the value of the quarter state. Then we can use the state in the code for that arm, like so. Okay, interesting. If we were to call value in cents, coin quarter US state Alaska, coin would be coin quarter US state Alaska. When we compare that value with each of the match arms, none of them match until we reach coin quarter state. At that point, the binding for state will be the value US state Alaska. We can then use that binding in the println macro expression, thus getting the inner state value out of the coin enum variance for a quarter. Okay, quiz. Consider these two implementations of a function decrement and unsigned number twice. The functions have the same behavior for okay. And none. Sum into the if n equals to 0, if n equals to 1, if n the functions have the same behavior for all inputs. Determine whether the program will pass compiler or not. Okay, either left to right. Hello world, right, hello world. Match hello world. Doesn't know. when lowered, and then length, value, length. So 1, 2, 3, 4, 5, 5, 6, 65 is 11. Boom, shit. What? Doesn't make sense. 1, 2, 1, 2, 3, 5, 6, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What? It's 11. I don't understand really. Oh, okay, so the X was moved here. So it's impossible to use here, X. Matching with option T. In the previous section, we wanted to get the inner T value out of the sum case when using option T. In the previous section, we wanted to get the inner T. We wanted to get the inner T. In the previous section, we wanted to get the inner T value out of the sum case when using option T. We can also handle option T using match as we did with the coin enum. Instead of comparing coins, we will compare the variance of option T. But the way that the match expression works remains the same. Let's say we want to write a function that takes on option I32 and there's a value inside, adds 1 to the value. If there isn't a value inside, the function should return the non-value and not attempt to perform any operations. This function is very easy to write thanks to match, and will look like using will look like listing 6-5 here, option and then none sum I plus 1 sum 5 5 and then pass to the plus 1 then plus 1 and then here and then 5, so 6 and then okay, makes sense. Let's examine the first execution of a plus 1 in more detail. When we call plus 1 5, the variable x in the body of a plus 1 will have the value sum 5. We can compare that, and we then compare that against each match arm. The sum 5 value doesn't match the pattern none, so we continue to the next arm. Does sum 5 match sum I? Why? Yes, it does. We have the same variant. The I binds to the value. Yes, here. Value contained in sum, so I takes a value 5. The code in the match arm is then executed, so we add 1 to the value of I and create a new sum value with our total 6 inside. Now let's consider the second call of plus 1 in listing 6-5 where x is none. We enter the match and compare to the first arm. It matches, there's no value to add to, so the program stops and returns the none value on the right side of arrow. Because the first arm matched, no other arms are compared. Combining match and enum is useful in many situations. You will see this pattern a lot in Rust code. Match against an enum. Bind the variable to the data inside, and then execute code based on it. It's a bit tricky at first, but once you get used to it, you will wish you had it in all languages. It's consistently a user favorite. Matches are exhaustive. There's one other aspect of a match we need to discuss. The arms patterns must cover all possibilities Consider this version of our +1 function, which has a bug and won't compile. We didn't handle the none case, so this code will cause a bug. Luckily, it's a bug Rust knows how to catch. If we try to compile this code, we will get this error. Rust knows we will get this error. Wait a second. I didn't handle the none. Okay, so cause a bug. Luckily, it's a bug Rust knows how to catch. The pattern none not covered. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last possibility in order for the code to be valid. Especially in the case of option T, when Rust prevents us from forgetting to explicitly handle the none case. It protects us from assuming that we have a value when we might have null, thus making the billion-dollar mistake discussed earlier impossible. Catch all patterns and the underscore placeholder. Using enums, we can also take special actions for a few particular values, but for all other values, take one default action. Imagine we are implementing a game where if you roll a 3 on a dice roll, your player doesn't move, but instead gets a new fancy hat. If you roll a 7, your player loses a fancy hat. For all other values, your player moves the number of spaces on the game board. Here's a match that implements that logic, with the result of the dice roll hard-coded rather than a random value. And all other logic represented by functions without bodies, because actually implementing them is out of scope for this example. For the first two arms, the patterns are literal values 3 and 7. For the last arm, that covers every other possible value. The pattern is the variable we've chosen to name other. The code that runs for the other arm uses the variable by passing it to the move player function. For the first two arms are the literal values 3 and 7. For the last arm, it covers every other possible value. The pattern is the variable we've chosen to name other. The other that runs for the other arm uses a variable by passing it to the move player function. That makes sense. This code compiles even though we haven't listed all the possible values U8 can have, because the last pattern will match all values not specifically listed. This catch all pattern meets the requirements that matching must be exhaustive. Note that we all have to put the catch all arm last because the patterns are evaluated in order. If we put the catch all arm earlier, the other arms would never run. So Rust will run us if we add the arms after a catch all. Rust also have a pattern we can use when we want to catch all, but don't want to use the value in the catch all pattern. Underscore is a special pattern that fetches any value and does not bind to that value. This tells Rust we aren't going to use the value, so Rust won't warn us about an unused variable. Makes sense. Let's change the rules of the game now. If you roll anything other than a 3 or a 7, you must roll again. We no longer need to use the catch-all value, so we can change our code to use underscore instead of the variable named other. Makes sense. This example also meets the exhaustiveness requirement because we are explicitly ignoring all other values in the last arm. We haven't forgotten anything. Finally, we will change the rules of the game one more time so that nothing else happens on your turn. If you roll anything other than 3 or a 7, we can express that by using the unit value, the empty tuple type we mentioned in the tuple type section as the code that goes with the underscore arm. Yes, tuple unit value. Finally, we will change the rules of the game one more time so that nothing else happens. So you turn your turn. If you roll anything other than 3 or 7, we can express that by using the unit value, the empty tuple time. Okay. That makes sense. Here we are telling Rust explicitly that we aren't going to use any other value that doesn't match your pattern in an earlier arm, and we don't wanna run any code in this case. There's more about patterns and matching that we will cover in chapter 18. For now, we are going to move on the if-let syntax. We're going to move on to the if-let syntax, which can be useful in situations where the match expression is a bit wordy. Okay. We'll pass compiler none. Okay. Location, point range, location range, 05, and then okay, 05. Location point, dop, range, yes. 5. So 5 and becomes a 5. It does compile and 5. Consider this method implemented for the option type. Which sentence best describe the behavior of this function? Self 30. Match self. This option. Returns a new option containing the object inside the self if it exists and otherwise. Insert other into self. Insert others into self if self does not already contain a value. Return the reference to the object inside the self if it exists. Return the object inside the self. Return the new option containing return the reference to the object. Return the object inside the self. Returns the object inside the self that exists. Returns the object inside the self it exists. Okay, makes sense. Last one. Boom, yes. Concise control flow with the if-let. The if-let syntax lets you combine if and let into a less verbose way to handle values that match one pattern while ignoring the rest. Consider the program listing 6 that matches on an option U8 value in the config max variable, but only wants to execute code if the value is some variant. A match that only cares about executing code when the value is some. A match that only cares about executing code when the value is some. Okay, some, yep. Okay. Some U3, U8, 3, U8. Okay. If the value is some, we print. If the value is some, we print out the value in the sum variant by binding the value to the variable max. In the pattern, we don't want we don't want to do anything with a non-value. To satisfy the match expression, we have to add the underscore tuple unit. And after processing just one variant, which is annoying boilerplate code to add. Instead, we could write this in a shorter way using if let. The following code behaves the same as the match in listing success. So let here, then if let figure max, if let some max. What is this? The syntax if let takes a pattern and an expression separated by an equal sign. It works the same way as a match, where the expression is given to the match and the pattern is its first arm. In this case, the pattern is some max, and the max binds to the value. Inside the sum. We can then use the max in the body of the if let block in the same way as we use the max. The body of the if let block in the same way we use the max in the corresponding match arm. The code in the if let block isn't run if the value doesn't match the pattern. Using if let means less typing, less indentation, and less boilerplate code. However, you lose the exhaustive checking that match enforces. Choosing between match and if let depends on what you're doing in your particular situation and whether gaining conciseness is an appropriate trade-off for losing exhaustive checking. In other words, you can think of if let as a syntax sugar for a match that runs code when the value matches one pattern and then ignores all other values. We can include an else with an if let. The block of code that goes with the else is the same as the block of code that would go right with the underscore case in the match expression that is equivalent to the if let and else. Recall the coin enum definition in listing 6s4, where the quarter variant also held the US state value. If we wanted to count all non-quarter coins we see while also announcing the state of the quarters, we could do that with a match expression like this. Coin, match coin quarter state, put println state quarter from blue state, and then state. Okay, makes sense. Or we could use an if let and else expression like this: count euro and coin quarter state coin print state quarter from blah and count +1. Okay, that makes sense. If we have a situation in which your program has a logic that is too verbose to express using match, remember that if let is in your roster toolbox as well. Coin. Expression and pattern. Expression. Oh, this was thumb 3 UA, thumb 3 UA, thumb 3 UA. Then 3 UA max. That makes sense. And in this case, coin is this exactly this pattern that has some state here inside it. So okay, makes sense. Which control flow construct would be most idiomatic to use in the following situation? Print a second field of range if LOC is a range. Print the second field of range. Print the second field of range if LOC is a range. Okay, location is a range. Print the second field of range. Print the second field of range. Second field of range if log is a range. Print the second field of range. If log is a range. So then if let location range equals LOC, then print second field of range. This second field, I guess. This means so I don't really need to care about other fields, right? So I don't then it's flat simply. Which control flow constructs would be most idiomatic to use in the following function? Return the first field of range or the only field of a point. Return the first field of a range or the only field of a point. Two things I should deal with here. Then I need to deal with everything, yeah. And I think the match is resolvers. Yes. Summary, we've now covered how to use enums to create custom types that can be one of a set of enumerated values. So we've now covered how to use enums. We've now covered how to use enums to create custom types that can be one of a set of enumerated values. We've shown how the standard library's option T type helps you use the type system to prevent errors. When enum values have data inside them, you can use a match or if let to extract it and use those values, depending on how many cases you need to handle. Your Rust programs can now express concepts in your domain using structures and enums. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions get only values of the type each function expects. Your Rust programs can now express concepts. Your Rust programs can now express concepts in your domain using structures and enums. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions. Creating custom types to use in your API ensure type safety. The compiler will make certain your function get only values of the type each function expects. In order to provide a well-organized API to your users that is straightforward to use and only expose exactly what your users will need. Let's now turn to Rust's module.